Hello everyone! I remind that our final goal is to understand how the macroscopic system of magnetic moments, or in other words, atoms of solids, which have magnetic moments, conduct in an external magnetic field, how to calculate magnetization and magnetic induction in this case, and so on. Let us begin with the case of one isolated local magnetic moment in an external magnetic field. We consider an isolated local magnetic moment μ subjected to an external magnetic field of strength h. In the case that this moment is associated with an atom in the solid, its kinetic energy is negligibly small, so that its total energy E is just an interaction energy U. Hence, the Hamiltonian takes the following form, where hatted μ is the magnetic moment operator. Taking a frame of reference with z-axis oriented along magnetic field, we have finally for the Hamiltonian the following expression. In the simplest case, when the spin is equal to 1/2, the operator of magnetic moment has only two eigenstates, corresponding to orientation of the magnetic moment along the z-axis, in other words, along the applied magnetic field, up, and in the opposite direction, down, respectively. Note that the electromagnetic moment is antiparallel to the vector of its spin because of the negative electron charge. The eigenvalues of the magnetic moment operator in the states up and down are plus μ0 and minus μ0 respectively. As a result, the particle with spin which is equal to 1/2 can locate it in two quantum states up and down, in which the projection of magnetic moment on the z-axis is equal to plus μ0 and minus μ0 respectively. And what are the eigenstates and the eigenenergies of the Hamiltonian? Since the Hamiltonian is linear in μz, the states up and down are its eigenstates as well. It is clear that E up is less than E down, so if the magnetic field is greater than 0, the ground state, or the state with the lowest energy, is the up state. This the projection of the magnetic moment on the z-axis is equal to μ0. At zero temperature, the system is always located in ground state. In other words, measuring the magnetic moment projection on z-axis at zero temperature, we shall always obtain μ0. And what will happen at non-zero temperatures? You can guess that the probability to find the system located in the excited state will become non-zero, therefore the mean value of μz will become less than μ0, because in certain measurements we shall obtain μz is equal to minus μ0. So our current goal is to evaluate the μz at non-zero temperatures. P up and P down are the statistical or thermodynamic probabilities to find the magnetic moment in the state up and down, respectively. Hereafter the Boltzmann constant is equal to 1. Calculating the constant C from the normalization condition, we have the final expression for the μz of t. So, we found the mean value of the projection of magnetic moment on the z-axis. Let us analyze the limiting cases. The first limiting case. If the magnetic field is equal to 0, the magnetic moment is 0 regardless of t. This is due to the fact that the energies of up and down states at zero magnetic field just the same, and both are equal to 0. So, the probabilities P up and P down just the same as well. They are equal to 1/2. Therefore, the states with the projections plus μ0 and minus μ0 are equally probable. The second limiting case. If the magnetic field is non-zero and temperature tends to infinity, then the μz tends to 0. Recall that μ0 is about 1 Kelvin by Tesla. So, at magnetic field is equal to 1 Tesla, we have μ0h is about 1 Kelvin. Therefore, the condition μ0h is much less than t is right even at 10 Kelvin. The third limiting case. If the magnetic field is non-zero and temperature tends to 0, one has μz tends to plus mu0 at h greater than 0, and mu-z tends to minus mu0 at h less than 0. And finally, if the magnetic field tends to 0 and temperature is finite, one has mu-z tends to plus mu0. For a visual representation of the temperature and magnetic field dependencies of magnetic moment projection on z-axis, we can plot the resulting graphs. They look like this. Note that in the case that magnetic field is oriented along the z-axis, the magnetic moment projections on x and y-axis are zero at any h and t. This is a consequence of zero values of quantum mechanical averages of the spin operators Sx and Sy in the up and down states. In this lesson we understood the behavior of one isolated local magnetic moment in the external magnetic field. So we found that in the simplest case, when the spin is equal to 1/2, the operator of magnetic moment has only two agent states corresponding to orientation of the magnetic moment along the z-axis, in other words, along the applied magnetic field, and in the opposite direction respectively. And if the magnetic field is greater than 0, the ground state, or the state with the lowest energy, is the up state. At 0 temperature, the system is always located in ground state, but at non-zero temperatures, the probability to find the system located in the excited state will become non-zero. Finally, our main result of the lesson is the obtaining and the analysis of the expression for the mu-z.